Pacific Northwest National Laboratory, which is located in the state of Washington. And I'm in Montana right now, not seeing the smoke because this summer it's blowing more toward the southeast and east, and other years it's blowing right over us. So I know what you're dealing with right now in the east. And in fact, scientists like Ken and his group, and scientists like me and the groups I've represented over the years, have been trying to do the opposite, to try to understand why the global climate is changing, exactly what drives that, and exactly how we could possibly maneuver ourselves to fix it. As a human species, we learned starting several decades ago that the humans on this planet have created enough impact to actually change the planet in many ways, not just its atmosphere. And so we've been working for decades to try to figure out how to treat the planet better and to have it remain as it was before we were here. Not that over geologic time, of course, it's varied wildly in terms of temperature and where continents are and so on and so forth. But we live in the present. That's what humans do. And we're really interested in what's going to happen in the next century or two and beyond. So that's where groups like Ken's come in. I'm a proud member of his group, and he's going to give you an incredible slide presentation of what this group is all about and what we hope to do in the future. So Ken, why don't you take over?
Sure, thanks, Andrew, and everybody for being here. I'm an oceanographer, 35 plus years at this. I've done nothing else. I've been mostly at Woods Hole Oceanographic Institution, Falmouth Cape Cod, about 1,000 people, and one of the largest international oceanographic institutions in the world. I'm in a chemistry department because I look a lot at carbon and nutrient cycling. And one interesting fact that I won't get into, but my specialty is radioactivity. So if you look up Fukushima and my name, you'll find a lot about our group running after these accidents and measuring what's in the ocean after humans accidentally put in radioactive isotopes. But some of those same isotopes help me study the ocean's role in carbon and climate. So some of the data that's behind these slides come from studies I've been doing for 35 years of carbon and how it's tracked by these radioactive isotopes that occur naturally in the ocean. So everybody in these fields was specialists. I worked 2 years at NSF, National Science Foundation. And I think what we're going to try and do today is walk you through a bit of how we introduce the topic of the need for carbon dioxide removal, the ocean's role, and then a bit on iron. I don't know, Andrew and Mike, I might do less on specific where we're at on budgets and what we have to do moving forward. But I think these first few slides at least will give you a flavor. I'm an oceanographer. Last thing I want to do is harm the ocean. But when we're talking about climates and a crisis, when we already are changing our planet, we're already changing the ocean. And what could we potentially do about that in a responsible way? Whether that feeds markets and someone makes money off of it, that's not actually my motivation at all. But we'll get into that in this group that we formed that's trying to move forward. So is that enough of an introduction, Andrew?
That's great.
So I'll get right to some slides that are now a little bit well worn because they were shown not too long ago. The first 3 are about 7 slides into, as I said, what I hope to convey. We developed some of this for like the COP meeting, by the way. I think it's kind of interesting perhaps to this group that Woods Hole Oceanographic Institution for the first time went to the COP meeting in Sharm el-Sheikh and made an oceans pavilion. And then the whole job was, when you're in between the countries of France and Japan and Egypt and the US talking about climate, is the oceans were there. What's going on here? And really the oceans play an outside role in our carbon system. And the title of this is from another talk I gave there about blue carbon and removal at gigaton scale. What do we understand about the need for carbon dioxide removal, the oceans versus land, because land has gotten more attention certainly on this, and can the ocean do more? And that's part of an academies group I work with about reaching out for how we might perturb the ocean to take up more carbon dioxide. So you're going to see CDR a lot, carbon dioxide removal, which is another way people used to talk only about geoengineering. Well, this is one type of purposely altering the planet to take up more CO2 in the oceans. So with that, this type of plot is a good way to get us thinking about where we are at in our climate system and what we need to avoid some of the massive heat waves, the loss and suffering due to climate, sea level rise, forest fires we've been talking about. And I'm sure you've seen variations on this. I use it to start to get to the scale that we're going to be talking about. And it's usually billions of tons of carbon dioxide emissions. We're about 40 in those units of what humans are doing. And it's been growing over time since the Industrial Revolution. Will continue to grow unless we start really actively, and this is where the Paris Accord and other agreements come in, reducing what we put into the atmosphere in a very deliberate way. We know how to do this. We can make a big dent in this. We can change the slope, all those scenarios, and they all have an impact on whether we can keep to 1.5 degrees or 2 degrees and potentially reverse that scenario. And the only way we're going to actually keep it at, I think, what's really well understood in the scientific community, maybe less in the public, is not only would we have to reduce emissions, but we have to think of ways, negative emissions, to take carbon dioxide that we've already released out of the atmosphere. That's because it takes hundreds or 1,000 years to get back out what we're putting in to stabilize climate again. So we have to be, within the next decade or two, developing technologies, and we'll talk about a few, to cause negative emissions. So how can we go from 40 being released to maybe less than 10 and taking out at the same time another 10 billion tons of CO2 per year? And that's where CDR comes in, carbon dioxide removal. So it's an essential tool to allow us to keep and stabilize our climate and hopefully reverse the loss and suffering we're facing now under climate change. And we do have a path, this path forward. I think we have a way to get there, but that's part of it. I don't really have to start my talk with saying we have a climate crisis. I think people know that already. I think what people don't know is if we went back to that graph and I said we're emitting 40 billion tons of CO2 per year, the emission side, okay? How do you reduce that down then? What's the scale that you would have to get to? Well, 1 billion tons is a very large number. And by that, I mean, if we look at our land-based solutions, how much of that could we reduce? Could we plant trees on the left there? How much land would it take? How many trees? Well, if you think about planting 100 million trees and growing them to maturity, they would collectively remove about 33 minutes worth of that annual 40 billion tons. It would make a difference. So you're emitting 40 billion tons, you can remove several hundred to 100 million trees, 33 minutes worth of your emissions. But now, how do you get it down even further? Is there room for 1 trillion trees? Do we still have to use land to make food for people? And as we convert land into forest, there's differences in the carbon cycle and storage on land that we have to consider. So trees alone are a hard way to reduce our annual emissions. Direct air capture, I'm sure this number was a surprise to me when I first heard it, but currently the largest active site is on Iceland, run by Climeworks, that removes 4,000 tons of carbon dioxide per year. It might sound like a big number. They're on a site where they can use geothermal energy to get atmospheric CO2 in these kind of wind turbine looking things and inject it, make it liquid, inject it into the ground underneath. But 4,000 compared to 40 billion, if you think of annually how much this would reduce our emissions by, it's 3 seconds worth of those emissions. So I hope people have heard of direct air capture. It does work. It has been verified, but that's a huge amount of energy and scaling up you'd have to do to impact climate. And people are doing it because it's kind of verifiable. It's an engineered solution, but a hard way to get to the scale we need of tens of billions of tons of CO2. So land works, engineered plants, but it's a hard way to get there. It's just not big enough. And that's the next graphic is more about, well, then, okay, where is there enough capacity to store all of this carbon? Well, you can see immediately when you put them on scales like this is now billions of tons of carbon. There's a number of 37,000 in the deep ocean and 600 in the atmosphere. So we're talking about a place that's 50 times more carbon stored in this deep ocean. In fact, all of our fossil fuel contributions since the Industrial Revolution would perturb this number by less than 1%. A few gigatons of carbon has been what humans have been releasing. And so we certainly need to consider the ocean if we're going to try and solve this question of where can we store more carbon to help with this planetary crisis. A number on here that I was surprised by when we first put it together was all of the land plants, all of the trees, all of the soils, everything. And again, they're taking up carbon through photosynthesis, right? And that's a lot of the ocean's role we'll get into. But that's 2,500. That's 15, 20 times smaller. So this deep ocean reservoir has to be considered if we're going to control climate or even understand where it's going to go without CDR, without purposeful changes. How much goes in and out of the ocean is very important. And another point on the next slide will be that the coastal blue carbon, people often consider blue carbon to be mangroves, salt marshes, and seagrasses, is a pretty small piece of the sponge, right? There's just not a lot of space to put more carbon. We'll see how much relative to growing trees and direct air capture on the next slide. But this is why the oceans are so fundamentally important. This is why the Ocean Pavilion was a very important part of COP, not because it covers 2/3 of our planet, the oceans. In fact, they are the single largest reservoir of carbon storage, hence regulate atmospheric carbon dioxide in a very major way. So let's think about what the oceans are removing already before we ask for marine CDR to come to play. The open ocean, you've probably heard, takes up something like 1/4 to 1/3 of our emissions. Thankfully, temperature would be much higher today if it wasn't, as the atmosphere carbon dioxide increased, some of that wasn't dissolved in the ocean. 1/3 of that emissions, those 40 gigatons, goes into the ocean. And think of this process as kind of like the reverse of your Coca-Cola bubbles. When you pop open that can, the gas comes out into the air. We're pushing so much carbon dioxide in the air that is putting that gas dissolved into the seawater through the process we call the solubility pump. So that's what the ocean does for us right now. I do want to emphasize here that there's all kinds of reason that the coastlines are important storage places for carbon, but in the same kind of criteria, how much of the annual emissions get into the coastal systems? It's about 5 days worth. It's in those seagrasses, salt marshes, but they play such an important role for fisheries, ecology, storm abatement, just human tourism. People enjoy the coastal ocean. So we shouldn't downplay this, but this reinforces the last slide. We've got to think big. We've got to think deep blue if we want to think ocean impacts on our carbon and climate. So that's kind of where we're at. And what happened to me in 2020 at the start of COVID, got the phone call from US National Academies about a committee that was forming to see, well, can the ocean remove even more carbon dioxide? A lot had been done. They actually had a report on land-based carbon dioxide removal, CDR, that included blue carbon. But the question was, what are the technologies out there now? And this is just 6 of them. We were given a particular task. And could we come up with a consensus on how important they might be in nudging that even further? Could we get more into the ocean? How would you do it? And we had a very specific task. 2 years, a year and a half of Zoom meetings. It wasn't the most fun way to do these. Typically, they fly you to Washington, D.C., but virtually we got 12 people together, looked at these six technologies, and we're going to get into iron because iron essentially is a nutrient. When you grow plants in the ocean, they kind of fall in 2 categories. The little guys, the Microplankton that take up carbon dioxide. I was telling someone in a prior call, half of the oxygen we breathe on this planet comes from those ocean plankton, those small microscopic plants. That's a huge part of our system. So could we enhance their growth rate to take out carbon dioxide through photosynthesis and get some of that carbon stored in the ocean, make that circle bigger, right? Could we grow more fish with ecosystems recovery, restore whale stocks? It's a slightly smaller circle here because there's just not as much room to do that. If you increase back to the whaling population, what they've heard before humans, you might get 100 million tons of extra carbon in their biomass, not billions of tons. But there's every reason to want to do ecosystem recovery. Seaweed farming has been around for millennia, particularly in Asia. Most people grow it for food stock. And could we scale that up, this plant growth up? And all of these on the left are called nature-based because they're using sunlight to get things to grow. And ocean tubes, a smaller circle that we looked at, not high on the list, but if you bring up water from deep in the ocean, you bring up nutrients as well. Typically what happens is things grow and die and bring that nutrient stock deeper. So there was kind of something in between, but these three look promising. The engineered solutions, that's more of, sort of like direct air capture. Maybe I'll look at electrochemical one that's a little bit smaller here. It has many similarities. You're taking power from the equivalent of hundreds of nuclear reactors. You need fossil fuel-free power, right? Because what you want to do is put energy in the ocean, split water into its components, including carbon dioxide, and bury that CO2 somewhere. Well, it's possible. Engineers are doing this as pilot programs, but that takes a huge amount of non-fossil fuel energy. We're nowhere near having enough clean energy to do this on a big scale. And one that we really won't have much time to talk about, but it's a very interesting idea that works on paper or in a beaker. How about that? Is you can put minerals in the ocean. You can grind up rocks like limestone and chalk, and that changes the chemistry. So more of what's in the atmosphere gets in the ocean. That solubility changes, but there's kind of a big difference in that if you're grinding up minerals like limestone, it's a 1-for-1 kind of deal. 1 part limestone gives you an extra part of carbon dioxide uptake. When we get to things that rely on sunlight, 1 part iron can give you thousands of parts. A little iron goes a long way of additional plant growth. It's not a 1-for-1 deal. Plants aren't made out of iron. They just need a small amount to grow. So there's big differences. And in this report, I'll take questions after this slide before we talk more about iron. But that's kind of to give you an idea of our motivation. We basically came up with a consensus. Now one of the top 3 downloaded reports in the Academy's history was looking at these because, as you know, there's been a whole industry developing around this and private funding coming in. But we said at the very top that we need those greenhouse gas reductions, that first slide. This doesn't replace that, but we also acknowledge the need for carbon dioxide removal. So greenhouse gas reductions, CO2 removal. We don't think any of them at scale would be 10 billion tons, that blue part of the curve, what we want to get to. But together, for example, iron, we could get up to 2 of those units we could get out. Maybe alkalinity, seaweed, we add another 2. We're going to get there with a blended approach. I'll tell reporters, if someone says they have the single answer for the climate or CDR, to run out of the room, because that won't work that way. It's too big of a problem. We have to acknowledge that when we move carbon dioxide removal up to larger scales, that's an intentional process versus doing nothing, which is also essentially geoengineering the planet, right? We are impacting the ocean in ways that are very harmful. It's warmer, it's more acidic, there's less growth because the nutrients are not mixing the same way. We have dead zones. So we have to compare our impacts with those that are happening already. They're intentional changes, and there might be unintentional things. Are we going to have growth of organisms we don't want in the ocean? And would society accept those impacts over the scenario we have now? We'll probably get to this term MRV, but if you were to have a deliberate, responsible path forward for CDR, how do you monitor that? How do you report and verify that? And on land, you might count trees, right? That's a little harder in the ocean, but I think we'll talk more in iron how we would do that. We have an example of that. But MRV, Bloomberg News just had something about the 3 most important letters in carbon dioxide removal are MRNV, and that's what that stands for. I think we've learned from prior experiments, we have a long history in ocean iron that we'll get to, that the field work itself doesn't cause permanent harm. When you do this kind of research, I've been involved in 30 years going out on ships, 20 years ago and spreading iron and looking for that response. I can show you some images of that. That itself doesn't cause permanent harm. It provides necessary data to choose where and when you might do this at what scale. And so even skeptics of CDR, invite them in to join our group. Let's understand how far we can push the ocean in terms of its ability to grow more of these plankton due to iron. Where shouldn't we be doing it? The scales are important, and the experiments are not the same as taking the entire ocean and adding in iron. This is a perturbation that's necessary. It's permitted under these international protocols. This is very specific, this terminology, London Convention, London Protocols, an international set of regulations. If you were to do something coastally, you'd be bound by what you can do within your state waters, your EEZs, your territorial waters. There's other permits. But the open ocean, the ocean commons, you often will get asked by people interested in this, well, who benefits from it? Why do you get to use this space that is really humanity's to determine what the fate will be of those waters? I think we have to acknowledge that cost is important, and the nature-based solutions on the left side of that graph tend to be cheaper than when you engineer a solution. So that shouldn't be the only reason you move forward, but that has to be determined. And we really don't know what those costs are when you start building these at scale. And then I do have a slide from our group on a series of ethical standards that we think are very important to set out right at the start of how we're going to do these in open and cooperative ways with the public involvement. We're taking the approach, this group, I'll talk about exploring ocean iron solutions, that this is kind of a ground up approach. We're not forming a company with venture capital and private engineered techniques that no one else can do except us. We want to make this openly available to humanity so we can solve this process. And so that requires a set of ethical standards that we want to move on. So the next 5 or 6 slides are specific to how iron works. What the heck is that? And why would that increase productivity? But I'll stop here if there's just some general thoughts on this part of the talk.
I think Cassandra, Scott, and Henry, if there's any just phraseology, words that were used, concepts that might be a little bit foreign to you, if they're presenting this to an audience that doesn't know anything about this, any feedback at all would be valuable. And I see Henry just unmuted, so I'll shut up.
No, so far so good. I mean, there's a couple of points maybe. I think I forget which slide it was, where you were showing like the 7 different places that iron is stored or carbon is stored. That was a bit tough for me to follow, but maybe at some point going back through it or getting a copy of it would help also, just to kind of identify some of those points that can be streamlined. But I mean, so far been able to follow it. So yeah, please proceed.
And we will share a PDF of these slides, absolutely, and comments back. Again, some of these, as we go further in the talk, you'll probably realize these are less for public consumption than just for people getting them up to speed. But these next few, I think, are pretty basic to the ocean iron question, because people really don't appreciate when you think of, if you're a gardener, right? Maybe you put fertilizer on your lawn or on your tomatoes, you think of the nitrogen and phosphorus. But this idea that iron is an essential nutrient goes back to this scientist, John Martin, who quipped, and this probably is the most famous oceanographer quote that I know of, but give me half a tanker of iron, I'll give you the next ice age. And I was sitting on the floor when he made that quip in the late 80s. That gives you a bit more of my background. And he was a geologist as well as a trace metal chemist. He could measure iron in the ocean better than anyone in the late 80s. But the curious thing he's trying to explain is if you go back 1 million years, this is 800,000 years, and you look at our greenhouse gas carbon dioxide and temperature, you know, when you say, we say, the scientists, we're very certain that carbon dioxide is a greenhouse gas, it's because of records like this in ice cores, where when you get lower carbon dioxide, we have cooler temperatures. And by the way, the scale on the right today is 400. This is before humans started mucking with this. But we had these fairly regular glacial, interglacial cycles, they're called. And every time we had lower carbon dioxide, John Martin, in those ice cores, and other scientists said there's higher dust. Well, who cares about dust? Well, that's where the iron largely comes from. It's all around us. It's one of the most abundant minerals on this planet. And so that's the concept behind what he was thinking. What's going on? How does this work in the ocean? And that set up a series of experiments in the 90s that were to go out and really just add iron. It was that basic of research. And the image, the photograph here is an icebreaker down off Antarctica. The key here is that if you get far away from land, you have less dust. So anything in the southern hemisphere, there's far fewer continents, and everything covered in ice doesn't generate a lot of dust. So this is a particular region that John Martin and others hypothesized would respond well to iron. And they could do this in little beakers and bottles, but when you spread iron behind the ship, something like this happened. It was just amazing how quickly, within days, plants grow very fast in the ocean. They might double their numbers in days or a week. They grow fast, they're small, but they grow very fast. So the green is chlorophyll, showing plant growth that happened in response to iron. And certainly, successfully, different groups around the world were doing these experiments in different locations. A group I worked with in the Southern Ocean, 60 degrees south, this is water around Antarctica as well, put in iron, and 30 days later, got this image from a satellite of this horseshoe shape. And from satellites, we can see chlorophyll, the same color, and here coated again green. But this was caused by the addition behind the ship of iron in this remote region of the ocean, where if you look all around it is blue. And so we were pretty proud of ourselves. We wrote a lot of publications. We got very far into solving the first part of the iron hypothesis, which is what limits growth, iron in these remote locations, not everywhere, but in many places, like not under Saharan dust, for example. The reason we're here today is thinking about a word, carbon sequestration, or CDR, carbon removal. How do we impact air, sea, atmospheric carbon dioxide? So the plants take up CO2 when they grow. When they die or eaten, some of that sinks down into the deep ocean. And the reason that's really important is kind of alluded to in these kind of graphics here, where if they live and grow in the surface, it's just like your lawn, right? You grow green stuff on your lawn, it grows, you mow it, or the winter comes here in New England, and all that carbon just gets recycled back when it decomposes. That's not a good way to change the atmospheric carbon dioxide balance. What you really need in the ocean is to bring that carbon deeper. We call this a biological carbon pump. And that might be the plankton that settle when they die. It's more likely to be something eats the plankton. Zooplankton are the bigger animals that eat the plants. Then you get small fish, larger mammals, but that food web creates material that sinks. And then you're talking decades or centuries, and you're talking something equivalent to planting a forest or a redwood tree, right? That's really important. And then my career has been built around looking at the natural systems and why some places are really inefficient. In some ways, nature knows how to use that carbon. That's a food supply. That's the manna from heaven. That's what's raining down to feed the entire ocean. This is really not the scale. This is 100 meters. That's 4,000 meters. This is the skim of the ocean where there's sunlight is where this goes on, but you're feeding the rest of the ocean. So most of that gets eaten, but some does get down. Could we enhance that? And if we do, why does that matter? That's because this word of durability comes to play. Again, grass won't be a good secure place to put it. Trees might be. Well, deep in the ocean, I think I'll just focus on I should probably just shown one of these, but if you look at different places in the ocean where we might do this, how far does that carbon have to go before it's removed for hundreds of years, or on the right, thousands of years in yellow? And if you look at the Pacific Ocean, this is looking down at 2,000 meters. The ocean, the Pacific is at 4,000, halfway down. We're only halfway down. But if you put carbon there, it would take over 1,000 years. And maybe you've heard of the Great Conveyor Belt. There's a general circulation that's pretty slow in the ocean that takes the northern Pacific waters and brings it back out to the atmosphere in the Atlantic. And so we have these things that we have to think about. Where is there the need for iron? How much carbon can we get? And can we make it durably sequestered if we're going to impact climate? We don't want to grow grass, we want to grow redwood trees. And I think we know this pretty damn well. We don't quite know that durability question. We don't really know where it's going. And so what our group has done, and I'll do two of these and maybe then take a quick break, but is, you know, maybe you've seen this. This was one of the links we formed about March 2022 to start talking with each other. This is now 50 international scientists, 25 institutions, about not forming a company, but could we explore, could we do the science that's needed to address the durability? How much gets how deep? Could we address how many billion tons this could be scaled up to? These are open questions. Could we look at those ecological impacts in a way that makes us comfortable as oceanographers, that we're not destroying what we're trying to do, which is remove carbon dioxide? And could we do that at a reasonable cost and following ethical standards that we think are key to using this common space of the ocean? So how do we do that? And that's what ExOIS is all about. Anyone's welcome to join us. You can get on our website, Ocean Iron. We made the white paper available in time for the COP last year. This summer, we're working on a very specific set of task forward and milestones and costs, and I'm not sure we'll get that far into it today. Depends on how long we want to go. But I do want to, before I kind of go quiet again, is just say a little bit about these guiding principles or code of conduct. You know, this has been thought about with genetically modified organisms, right? This has been thought about with some of the human genome research. We really want to do this in the right way. And to us, that means open and cooperative research. For scientists, that's very much in line of how we do our own work. We don't set up barriers for cooperation. We do want to do this for the benefit of humans and the environment. Otherwise, I wouldn't be here. I could retire tomorrow, but I think there's a reason we're doing this. If someone makes a buck down the road to make this happen, that's fine. But that doesn't motivate ExOIS. We're not selling shares in this company, for example. We do need independent groups coming in to say that what we're doing works, so we need to evaluate that iteratively. We need more than one experiment, is what this says. And something we didn't do very well maybe 20 years ago is right from the start, we really want to have the public have a better awareness of what the options are, why we're doing this. This is not, you know, necessarily the mad scientist going out out of some hubris to think we can change this planet. If we're responding to a crisis, the first bullet here, and if we can't do something for the benefit of humanity, we shouldn't even be out mucking with the ocean. And so, yeah, I've got a few more slides.
Well, Ken, if you could just pause there just briefly, I just want to get Henry's input, because I know last time we spoke, the word climate was one that we wanted to avoid. How do you feel about that the wording of that fifth bullet there? climate intervention. I haven't heard that before. I mean, it's intriguing.
Yeah,
Yeah, I mean, so much of it, again, depends on the audience you're talking to as well. I've just learned to be extra sensitive to it, knowing that a lot of the clean energy companies I help do a lot of their development in places that are highly skeptical of climate change, to say the least. So that's why I've become so sensitive to it. So a lot of it just depends on who your audience is. It's not to suggest that it isn't real or, you know, it needs to be avoided. I think we just need to consider audience when we use it. Engage the public. So, you know, climate solutions. And let me ask you this: does iron fertilization, does that fall under the nature-based solutions category that you mentioned earlier?
yes, it does, because it's a growth of a natural plant that's already there. Yeah,
Okay, so I would consider, you know, language like climate solutions or, you know, nature-based solutions, something like that. Again, even if you're talking to policymakers on Capitol Hill who come from red America, things like climate intervention can be jarring to them. So so that's that one point. And then I would say just broadly, I mean, it is very educational. I've learned a ton. I think the things that stuck out to me were, I think I heard you mention estimated 2 billion tons of CO2 removal just through iron. Is that correct?
yes, per year.
Per year. Okay.
Yeah.
So I would make that a prominent slide. It just helps people, it gives people kind of a tangible understanding of what success looks like. And then I would equate that to however many coal power plants, you know, however many gas powered vehicles you're taking, you know, you're offsetting. Give it something people can kind of visualize that, okay, this means 200 coal power plants or 200 natural gas power plants aren't needed, something like that. That just kind of helps, you know, kind of ground it in their world.
Yeah.
I think is good, and says, okay, helps them feel like that's something I can get around or get behind. So that's number one. Number two, I think overall it's very good. I generally kind of like to streamline the number of images that I have on each slide, just knowing the way brains work, especially my brain. The more streamlined the information is, the better. Especially if you are a beginner. If you're somebody who cares about climate solutions, who cares about, you know, protecting nature, but has no scientific understanding or no, you know, basic context in this potential solution, I think kind of just generally streamlining how much information is thrown at them visually. Number one, it helps them process what you're presenting visually, but also makes it easier to also follow along with your oral remarks. And then what else? So on that last slide, I think it's great you had the call to action to visit the website. I think that's great. I would even encourage going one step further and kind of giving them a very specific call to action of joining your email list. I'm assuming you have one. I should have checked beforehand. I don't know.
Yeah.
The reason being, you can capture people more effectively that way. Somebody could go to a website for 10 seconds and then they're gone and you never see them again. Whereas if you get them, if you're very clear that we want you to sign up for this newsletter, that way they're captured. You've got their email list, and you can then start to make, it's what we call the ladder of engagement, where you start seeing who's opening your emails the most, and that tells you, okay, that person really cares, so let's talk to them to see if we can get them to do X, sign this letter to policymakers or whatever it may be. So that way you capture them, and then you can kind of start working them up that advocacy ladder. You can do it with social media as well, but I think email is the best call to action. And then just generally speaking, I don't have a solution to this yet, but I think we talked about this on the last call, always looking for ways to kind of localize this. I know that's hard to do when we're talking about something that's occurring in the middle of the ocean, thousands of miles away from most people. But if there are ways to kind of think about how it affects, whether it's seafood supply or, indigenous communities or anything that just kind of helps to localize this for at least some communities, some audience members that we're going after in our priority audience, I think really helps. Like, why does this matter to you? If you were to have a slide that's, headline, why does this matter to you? What would be on there? In addition to, climate solutions, what else would be on there? Maybe it's seafood supply, maybe it's maritime industry. I don't know. But I think that's worth exploring too.
Sometimes we'll talk about, rainfall farmers in the Midwest need this. This is what's affecting their crops, right?
Right.
So,
That's a great example. Yeah.
And the crops can be burning up or they could be flooded, but it's all from the same source, and perhaps they don't understand that.
yeah, and
Those
once you
are my initial observations, but otherwise, I'm very educational.
thanks. And like what you said, the audience and the amount of time we have. And so speaking of time, do we want this to end on the top of the hour, Andrew, et al? Do we?
Well, I mean, we're recording it, so you can go as long as you need to, and we can then chop the video up later. And if everyone falls off, and it's just me and you, we will chop that up, and all they hear is your voice and slides. So go for whatever you need. And folks, if you do need to drop off for whatever reason, feel free to drop off.
Because the next part of this, and I think I'll go a little quicker, but it's more about where this group feels we have to go in the next 5 years for building up a program to answer those questions. So this isn't intended necessarily for public audience, but I was showing it back to groups who weren't at this meeting just 2 months ago. But one comment might be that, this is a group of really eminent scientists who gave up a week of their time to help plan what we should do next. And we were thinking of what do we do in the field that we didn't do 20 years ago? That's a question I get asked a lot, by the way. Why didn't we learn enough? And what I tried to emphasize was on that picture with the grass and the redwoods. No, we didn't really go deep enough, long enough. So we're talking about leaving this meeting with a plan for those next generation experiments. That's really what we set out to do. We also took one of the 4.5 days to think of social governance and financing issues. How do we make this happen? How do we bring in the stakeholders, the local fisheries, the native populations who are in a given area, whether they're working on the docks that supply the boats or whether they're thinking about the salmon they're taking out of the Gulf of Alaska or something like that. So we covered a lot of topics. The type of nerdy science that we got into was about what would that field experiment look like? And so I'm going to go pretty quick. Again, not trying to teach you everything, but there are places where we think this will be more effective. And so when you look at those locations, whether it's around Antarctica, we actually are preferencing this area here. The reason I mentioned Alaska is in the northeastern side of the Pacific, that we could do a deployment of something that released iron, say where the star is. We know ocean currents well enough to say where it would go. And we would use models and other existing knowledge to say, where could we put things that measure carbon in different ways? And this is, again, I could give a whole talk on sediment traps. That yellow triangle is a rain gauge that gets anchored on the bottom. And as those little marine snow particles settle, they capture that. And I could put that at my 2,000 meter depth, right? I could measure everything that gets here is going to be here for at least 1,000 years. So we were nerding out on how you might monitor something like this to create an observatory. Gliders and floats, cool things are happening in ocean sciences and the technology side. I've spent 2 years of my life on ships, so I don't need another day, to be honest. I don't go on cruises. Well, we call them research cruises, but I don't go for pleasure on a boat. But I want to be putting out, fleets of these autonomous vehicles, gliders we call them, that move up and down with very little energy, just changing their position so they're more buoyant going up, less buoyant going down. They can make chemical measurements, biological measurements. We can put in things like at the lower image is a float that goes up and down vertically. And those particular devices have chemical sensors and cameras. They can take pictures of those little phytoplankton and then on board tell you who is there. You don't have to pull a net through the ocean. So this is a bit of the nerdy part, but it was getting down to the nitty gritty of what that experiment would look like. I think it's good to see that here. What we end up with in terms of scientific data is you might make measurements. I might put in a line of these in the ocean. Somewhere in the middle, they're going to have the biggest effect. On the edges, we shouldn't see any effect. And that's what we call additionality in the terms of the carbon world, is how much carbon was put deeper in the ocean because of what we did, adding iron, compared to a control. That's the classic science experiment. And again, I'm not using these necessarily for a general audience, but I think it's good for you to understand that there will always be some carbon sinking. It's maybe not as straightforward as planting a forest or not, but it is a little bit like what was there before the forest and what did you plant that's going to increase the amount of carbon that's removed. In this case, we're putting our sediment traps in the water to measure that north and south of where we put it in. And then this kind of concept, it's a bit more for the markets and for where this could be used and how we might do this, but we're going to perturb the ocean to take up additional carbon, the difference between those two lines. And that's going to take things like sediment traps or my gliders and floats. And I think oceanographers know how to measure that already. We're going to do better. But we also need to rely on those models, those maps of the globe, to say, hey, Ken, if it gets to this depth, 1,000 feet, 5,000 meters, whatever, it's going to be there durably. It's going to last for a long time. And that's important for climate. And both the observationalists, that's more my field, and the modelers who were there, think we can do this with some confidence. So you could then be presenting to policymakers, to markets, how much carbon was removed for more than 100 years. We call this a centennial ton. We try to come up with metrics. What are you doing? Well, we're perturbing this system and observing that. We're predicting and measuring where it goes for how long. And so we might say that of the 100,000 tons that we remove from the surface, 20% of that's going to be secure in the deep ocean for greater than 100 years. So we've created 20,000, or did I do the math right? 200,000 centennial tons of carbon. And that's what the market would need if that's how you were funding this. That's what the modelers would use to say, what is the perturbation? And you would do this in multiple locations and you would adjust for some things. But we think we have a way. We had several people there from the carbon market world and from a company that used to do ocean iron, potentially as a marketing approach for selling credits, that felt that this would give them the ability to turn the scientific data into something that markets could use when you look at all of these curves together and you say, how many tons did you get next time, Ken? And we can get us there. So that's a kind of a nice conceptual step forward. And yeah, I think, so that's a little bit of a knowledge thing. I'll probably have to move fast, but I think one thing about our group is we call this an inflection point because we went in thinking all we're going to do is talk about what to do in the field. And we think the Northeast Pacific is the best, but we can talk about bigger, longer experiments, looking at durability and ecological impacts. Again, we're going to put in the next 2 months numbers on these, how much they cost, and what does that really mean in 5 to 10 pages. And where we will need help, I think, is when we're done with that document, that's maybe 50 pages, take these 5 things back and make them into the 1-page infomercial, right? What does this look like? We need to have models that help us plan those experiments, how many of those traps, and extrapolate into the regions where we're working. We need to test, we call it the bake-off. I think of the Great British Baking Show, what's the best flavor of iron? And Mike is here because he wrote a paper in Nature that got a lot of publicity because they have a really cool form of iron that's 10 times better than what we've done before. So we've got to be working on these things all at the same time. And partly why we're talking to Andrew and others in the group before is how do you fund this type of experiment? How do you deliver that with a plane or a ship? What type of technology? I showed you 3 little postage stamps of technology to measure carbon that's sinking. Those floats and gliders measure the EMRV, something we're really trying to stress.
Well, Ken, if I could just pause you for 1 second, going back to the bake-off piece. So for Cassandra, Henry, Scott, this would be sort of like a challenge, like we did the Deep Space Challenge. So we know there are gaps out there. We need to fund them, get them set up as quickly as possible for the incubation acceleration process. So that's what we're referring to there. And Ken did mention that was an area of great interest of mine because that does play in a lot of things that I'm fascinated with.
So the other ones include the technology. And one thing we're trying to do, and the reason it's in red here, is most companies that are getting venture capital are really focused. Bloomberg had on their site recently, the 3 most important letters in CDR are M, R, and V. And all they talk about and the companies and their business models is counting carbon. And that curve I showed you falls into that. We want to know how much carbon gets out. But we're really stressing, our group and a few others, that it's really the ecological environmental impact. We don't want to start another fossil fuel industry that became wealthy but didn't have any responsibility for the impacts of releasing greenhouse gases. We don't want to make removal of carbon dioxide into the next environmental disaster, right? And that means really spending as much effort, and sometimes it takes more money to measure ecological shifts over years and decades and environmental impact. So there's a lot of science that we think needs to be done here and development. We don't have to wait for the first experiments, the new ones. And again, think of these pilot studies as a way to de-risk this, show the world we can do this and not harm the ocean, not create harmful algal blooms, not kill off fisheries. But all along, we're doing these things in parallel. This includes social scientists that were at the meeting helping us think about who are the fisheries stakeholders, who are the native peoples if we did this off Alaska and Canada. How do we get permission to do this under international law, because we would be outside of territorial waters. And I've got to build up an organization to make this happen, this office that would be housed at our Woods Hole Oceanographic, a non-for-profit research organization. We think that builds in some credibility here. Where I work will not endorse only iron, but it's one of the climate solutions that our director is helping support through his funding. And, I don't know, Andrew, if we have to get into costs, but, the most expensive part of this are those field programs that are tens of millions of dollars. And that's important to find those sponsors early on, because then we can start bringing in the models, the iron, the technology, finding permits and stuff. So we've got to get there. There is some early money on the scale of $10 or $4 million to basically do the bake-off, do the models, to get more people involved. Social science and governance, really, the first person I would hire if I knew we had at least $10 million is someone to go apply to the EPA for a permit. There's a process through the EPA's dumping office. Even though the US hasn't signed on to the London Protocol, we would follow that international set of standards and provide an impact assessment to get approval to do this kind of work. We need that kind of money right away, and a way to organize and have meetings like we had that was so productive. So there's a budget side. There's a 10-year timeline to get us about 5 years to the point where we have enough knowledge to do these larger observatories with all of these sites being studied. You can't just do one, but we'll start in that northern eastern quadrant. A pretty deliberate decision because the water there is the right conditions. It doesn't move as fast as in the equator. We don't have the storms like in the Southern Ocean, but we do need to get to a point where we could start doing this at multiple sites. We think it would take about 5 years. And that's really after that point where you can pass this on, say, whether the operational authority is some international body or companies that want to follow our protocols and measurement routines to do this in a responsible way. And so that is kind of how far off we're looking, but it's kind of the first 5 years. And I think that was kind of where we got. We're thinking of who is the host. We have offices like this. This is maybe, again, getting beyond certainly a public talk, but this program office would take in money and give it back out, interact with other programs. And I think I don't want to get too far into this, but we do need funding. We do need a structure. And what we're trying to come up with as a follow-on to the white paper will be those 5 specific things and their costs and deliverables and timelines that with your help and others, maybe we can, start selling off to, Department of Defense, private money, philanthropies. We've been talking to many different groups, a lot of interest in agencies, international sources and things. So I think that's probably a good place to slow down and stop and really turn this off. Get some more feedback. How does that sound?
That sounds good. Scott, I know your camera's off here, so I hope you're listening, but I did have a phone call recently with the state of Maryland, and they expressly are looking for MRVs for land-based CDRs, just to be able to measure that. So keep that in the back of your mind. We'll discuss that more this weekend.
Sounds good. Well, thank you for putting this together. This is completely new to me, so it's very educational.
I think something we can also use help with is, there's pressure from the public, hands off the ocean. So some of the messaging deals directly with that. But part of it is there's been groups that go out and oversell these things too, who are saying, we have an answer. We have a solution. And people won't know the difference between our group that wants to do this deliberate, careful experiment and someone who rents a fishing boat. This was done in 2012 off British Columbia, and go out and dump iron by getting $3 million out of a local native group there that wanted a better salmon return, and they never showed that they could do that, but they're still out there. And so one of the slides said the good OIF people, how do we keep on brand? How do we distinguish this umbrella of scientists who want to, I'll call it, do it the right way, for lack of a better word, versus people who are out there now proposing things. It's far cheaper just to get a fishing boat and dump some iron. It's relatively cheap. And there's examples of that bad behavior too. And we want to keep ahead of that and message ourselves. So we're the model, we have protocols, and if people aren't following our protocols, they shouldn't be getting paid for it, that's for sure. And by international law, they shouldn't be allowed to do it. That's another thing.
Yeah, I mean, I think to the extent those standards are in place, or, and, you don't envision them changing anytime soon. I mean, to the extent that you can even A, communicate those, B, kind of come up with a graphic or an image that shows what they are, I think really furthers your credibility. Obviously, I suspect you've already got it with a lot of folks given your career doing this, but I think especially for those who are new to it, I think demonstrating that you have thought hard about what the standards of excellence and best practices should be, that should be met, I think kind of helps you differentiate from those who are just kind of pursuing this headlong for commercial or other gain. And then the hands off our ocean folks, I butt heads with them every week, it seems like, and needless to say, their minds will never be changed. There's no persuading them, and that's okay. I think the goal is to also kind of inoculate yourself against them by finding advocates as well locally in key markets who who can serve as the competing voice of why this should be pursued, why it's the responsible thing to do, so that they're not, the Hands Off Our Ocean folks are not the only voice locally in the community. And that takes time. It means going on a roadshow and talking with, local Sierra Club chapters and nature conservancies, and you fill in the blank. It is quite literally a roadshow, and it takes time and getting them on board, educating them, getting them to understand it, and then also being willing to kind of serve as the counter voice of why this is the responsible thing to do.
Henry, it's Mike. Sorry, my camera won't come back on, but going back to these folks that are Hands Off Oceans, is it just, oh gosh, I hate to use the word, but ignorance. In other words, they just don't realize that humans have been abusing the oceans for as long as humans have been around, using it as a garbage can and many other things. And it sort of peaked in the 1950s when we were dumping radioactive waste from places like where I work at Pacific Northwest National Labs in barrels into the ocean, just to use it as a garbage can. But in this case, you mentioned it before, and so did Ken, these nature-based solutions. When a volcano goes off and all the smoke that comes out, it's not smoke, actually, they're very fine mineral dust, and the mineral dust contains iron, and that lands in the ocean, and then you have a phytoplankton bloom, which is perfectly a natural thing, and that's going to pull down a lot more CO2 from the atmosphere. Or a dust storm from Tibet that goes off to the east, and it crosses the Pacific, dumping dust all the way along its path into the oceans, and then across Canada, and then to Greenland. I mean, that's how far this dust goes from China, for example. All of these things are producing phytoplankton blooms along their path. So this is very much nature-based. And so what Ken's talking about is, okay, instead of having a volcano or dust storms have all the fun, people are going to go out and do this a little bit more, just like nature does it. And so do people in the Don't Touch the Oceans, they understand arguments like that, or will they still give you grief?
So two things. Number one, that's very interesting, and I did not know that, and I would consider finding ways to include that in your presentation, that ocean iron fertilization has been happening for millions, billions of years, whatever.
Yeah, the answer is billions. Yeah.
So I would give those examples. So this has been happening for far longer than any of us have been around. We're just supplementing. So that's number one. Number two, with respect to the Hands Off Our Ocean folks, part of it is extremely myopic. I can think of one lady in particular who just decided 20 years ago that there should be no human intervention in the ocean, and she doesn't care what comes along or why, but she's just kind of stuck with that. There are other folks who are using the ocean not because they care about it, but because they want to protect the property values specifically. So I work with offshore wind developers. And so there are folks who are concerned that there are wind turbines that you can see from 20 miles away, it's going to hurt my property value. And so they are now out holding Save the Whale signs out on the beaches, not because they care about whales, but because they want to protect their property value. So I think that gives you a good indication that they'll use whatever angle they need to protect their own self-interest. So that's kind of where this all comes from, at least from the narrow vantage point I've had with respect to offshore wind.
Mm-hmm. Okay, that helps. Thanks for the examples. It really helps me envision this.
Yeah, so they're very cynical or pragmatic, whatever term you want to use, where if whales is the issue they need to use, they'll use it, even if they have never cared about whales before.
Mm-hmm. Okay, thanks.
Yeah.
Good to know.
Yep. So I suspect, and just to add on to that, when you mentioned Alaska and fishery stakeholders, you probably already know this, but the fisheries community, particularly commercial fishing, is very territorial. In my experience, they believe the ocean belongs to them, in my experience. So I think it's reasonable to expect that you will encounter some of that. They'll ask questions, well, what is this going to do to the fishery stock? Are we creating mutant fish here? Like, as ridiculous as that may sound to the scientists on this call, those are, I'd be willing to bet money you'll get questions like that.
Mhm.
Well, it's not ridiculous in the sense the groups that I think are exaggerating the potential and selling, iron to this group of British Columbia, they're promising a higher return on the salmon. So if you increase the base of the food chain, yes, you'll get more plankton, more zooplankton, more small fish. It will work its way up. We don't have any evidence of how far that's going to go, but you could also create a food chain that's all jellyfish, right? You can create something that you no longer have salmon growing, you have something else, but it isn't a hard one to show data for. And so the people who don't care about data just say, yeah, this is going to work. And they call it ocean restoration or ocean pastures. If you ever see those words, we're not using them because we don't want to call this restoration. We don't want to call it an ocean pasture because that we think requires a level of knowledge about fisheries response that we just don't have yet. But most people think that would be good. By the way, the one bad thing, again, I said jellyfish, but harmful algal blooms creating toxic diatoms that grow in response to iron, produce the chemical domoic acid that causes some of the coastal, like California, toxic algal blooms. And we certainly would be measuring to see if that happened. It's never happened, but a lot of pushback 20 years ago saying, we're going to create another HAB, a harmful algal bloom. Everybody knows that's bad. And so we're growing pinnate diatoms that have that ability, but have not done that in the open ocean. So there's a lot of messaging around that. So what I find maybe in response, Mike, is there's different audiences in the public have different things they're scared about. They could be scared about HABs. They could be scared about deoxygenation. There's a group of my peers who don't want us to do this, going to put more carbon into the deep ocean. My God, the last thing we want to do is get more carbon down there. So those deep sea corals would now become more acidic, right? This ocean acidification idea. And we're making the surface very acidic now with carbon dioxide. That's not good. Shellfish and corals don't grow, but we're pushing the problem down deeper. But I think what we also have to realize is, and I'm not sure how to message this, but if you could save the Great Barrier Reef and humanity by pushing that carbon down faster than it's going to get there already, wouldn't that be a good thing at the expense of a 10% change in the stock of deep sea corals? I mean, there are winners and losers in these things, and there are groups that have really set their blinders and said, we don't want a single more atom to get into the deep ocean. And one response is, well, wait 1,000 years. It's going to get there anyway. Everything humans do. Whether humans will be here in 1,000 years, I don't know. But if we could speed that up over decades, that would be a positive thing. And yes, it will mean a more acidic deep ocean. But boy, that number there is so big, it's going to be a small change compared to the surface, where we've effed up things so fast that we're really damaging coral ecosystems, fisheries, and other things. So it's weird. The people you see that are, say, against this have lots of different motivations too.
Yeah, just what Henry was saying. Yeah.
Well, I've seen this twice now. I think, Ken, I could probably be one of those roadshow guys that
Yeah.
could deploy to the Sierra Club, and I could just parrot what you said and point to the slides.
There you
This
go.
is wonderful.
Find
Yeah.
out.
Henry,
You're welcome, Andrew. Just do it.
indeed. And Henry, as usual, your inputs are just invaluable.
That's
Deepa,
I'm on mute again. No, while this was going on, I've been doing some edits to your PowerPoint based on these two conversations that I know would clarify it for me, but there'll be suggestions for you to look at.
Okay. Yeah, always helpful, always being modified. This is great. And we'll have something in a couple of months that will be another kind of white paper scale document that we could use some help on how to turn that into the 2 pages, 5 pages, and pitches that we really need to hit up those foundations, those agencies, and that's something we can definitely use your help on.
Good. Yeah, we got a few thoughts as well. So Dave, I'll put the notes in there too. But yeah, overall, it's phenomenal. I mean, I think probably Ken, you probably feel pretty good too now. You've got a few practice pitches under your belt here. You got some big audiences coming up. Take that feedback and really knock the cover off the ball.
Yeah, well, this, I've got about, anyway, you don't want to know how many times I've given variations on this talk, but it's definitely a challenge, but I think it really, most people get it. We've had really positive, and I'll just bring up the COP event where we went in front of this very, climate oriented but non-oceans audience and really tried to have to convince them that the ocean, hey, has an outsized role here, and we ignore it at our peril if we're going to come up with climate solutions. And this idea of 30 by 30, you hear about a lot of these things that people want to do. That was proposed at one of these meetings really is protecting coastal blue carbon and not solving the climate. But we want to really say, hey, we've got another part of the story that's important here, and just bringing the awareness that this exists. We don't have the solutions yet. We use solutions more than intervention when we're talking to that group, because they really need to see that, and convincing agencies and governments that it's more than just monitoring. This came up in the last call, the ocean and how it's changing, but doing something about it. That's what ExOIS, that's what some of the seaweed programs and iron are about. And my experience, we don't gain from shooting each other in the foot within my community. There's a tendency to say, we're better than you, we can grow seaweed, we can put in alkalinity. But I think what we're trying to also do, which I think is better than 15 years ago, is say, look, that's great, go do the alkalinity experiment, go grow seaweed, but we're a decade or two ahead of the others in terms of what we're ready to deploy. And I think that's key for the urgency of this problem. So those are the type of things I think about when I'm trying to message this to different audiences.
Mhm. Right.
Well, I think it was good. I'm very happy. And this was recorded because I do know there's some other key stakeholders that had said they would really want to be here and are not here for whatever reason, but we'll pass this along to them to get some feedback from them as well.
Sounds good.
Yeah, and if this was super helpful, so thanks for the invitation. And I think it's a great concept. If it is possible to share a copy, I know if I take a second look through it, I'll see more things. Obviously, I'll keep it to myself. But if you can, that'd be great. And I'll send over any additional ideas or suggestions I have.
Right.
Thank you, sir. And Scott, I'll see you Sunday. Just bring a hot dog. We use that for catfish bait.
Sounds like a plan.
Sounds good.
All
All right. Thank you, Ken. Thank you, Mike, Henry, Deepa, Scott. You guys all the
Bye,
world. Thank
guys.
you.
Thank you.
Thank you.